Welcome back to the classroom. This is Mr. Wong speaking. We're going to go through the 2005 HSC Physics paper, question 16, with 5 marks. This is going to go through Module 5, Inquiry Question 3, and off we go. So from the nearest to the furthest, the 4 satellite moons of Jupiter, first observed by Galileo in the year 1610, are called Iowa, Europa, Ganymede, and Callisto. For the first 3 moons, the orbital period of each is exactly twice the period of the one orbiting immediately inside it. That is, if we say Europa, its orbital period is twice the amount of Iowa. Ganymede is twice of Europa. The mass of Jupiter is 1.9 times 10 to the power 27. The orbital radius of Iowa is this value here in kilometers. Use Kepler's law of periods to calculate Ganymede's orbital radius. Okay, so using Kepler's law, it'd be R3 or R cubed over T. We have big G, we have big M, we have 4 pi square. So just confirm that. Yep, 4 pi square. Okay, so we're trying to find R. We want to know what T is here. Okay, so we're not given the orbital period of Iowa or Ganymede, which means that we actually need to find the orbital period of Iowa first, and then using this relationship, find the orbital period of Ganymede. Okay, so our main objective firstly is to find the orbital period of Io. Okay, so formula we're using as we wrote here. So we could rearrange the equation first, or we can do our substitution. Let's go with substitution first. Firstly, convert all your units to the correct SI units. 6.67 times 10 to the power minus 11 times mass of Jupiter, and then 4 pi square. Okay, so according to this, it should be, so the radius will be times over here. To get t as the subject, we have to inverse both parts of the equation. So it looks something along the lines of 4 pi square times 4216000 10 to the power 3, 6, 7, 11 times that. And this will be the time period of Iowa, and then we have to times it by 4 in order to find the orbital period or the orbital radius of Ganymede. Okay, don't forget to cube the value. I forgot that in my working out, so thankfully I worked that. So the period would be seconds. So that's the orbital period of Iowa. And then we need to find the orbital radius of Ganymede. Just to help ourselves out here, I'm going to use a different color. Okay. Key note is that gm over 4 pi squared is a constant value. Okay. So r cubed over t squared, that is equal to this constant. So we can rewrite this into r3 io t io. Look at r3 Ganymede and t Ganymede squared. Okay, So that's what we have here. Okay, so the next thing is to know what's the time period of Ganymede. So this value we have here, if we times it by 4, that would equal to the time period of Ganymede. Okay, so if I rearrange this equation to make the radius the subject of the equation, I will get the following. So it will become t equals to the square root, and it's basing off this formula rearranged in this particular arrangement. So it will be the radius, well, actually we're trying to find radius, sorry. Okay, so we want to find the radius of Ganymede. So the period of the orbit comes up here. What we do also know is that the period is 4 times of Iowa. Okay, so if I just rewrite the equation, it'll be 4 times the period of Iowa square times the orbital radius of Iowa cube over the radius of Iowa, or the time period of Iowa square. So let's find our value here. And again, don't forget root 3. Okay, so using all those substitutions, and our arrangement is now correct. The total radius is this value here in meters. Okay, so it's about 1.07 million meters, I think. Oh, kilometers, that is. So this is the term in meters. That is the orbital radius of Ganymede. The actual question itself is not overly complex, but does seem like quite a lot of steps. So there you go. Next is calculate Ganymede's orbital velocity, or orbital speed. This is worth 3 marks. So the formula for orbital speed is gm over r. And if you do your substitution, times the mass of Ganymede, not the mass of Ganymede, but the mass of Jupiter, which would be 1.9 times 10 to the power 27, divided by the orbital radius, which we now have in meters, and just substitute that. That will give us our value in meters per second. Okay, and we get a value of 10922 meters per second. If we want to round this off to 3 sig figs, that would be our orbital velocity or speed. Alright, if you found this video useful in explaining how to go through Kepler's law and orbital speed, hit that like button and subscribe if you haven't done so already. Take care, and I'll see you next time.